In the previous lecture, using row and column reduction operators over an Euclidean domain, we proved the following theorem. So we showed that if D is a Euclidean domain, for a given n by m matrix with entries in this Euclidean domain, we can always find some elementary matrices U and V with possible permutation matrices as well that we denoted by E sub n plus minus and E sub n plus minus, so that when we multiply A by U inverse and V inverse, we end up getting this simple form for the matrix. Alternatively, we can say that using the row and column reduction operators, we can end up with this simple form for the matrix A. So we call this a Smith normal form of A. And moreover, this diagonal form consists of entries D1, D2, dr, and its diagonal entries, so that the first one divides the second one divides the third one, and so on. So after doing row and column reduction operators many times in an algorithmic way, we can end up getting this form. And as I've mentioned, this is called the Smith normal form of the matrix A. If you remember, the way that we did it was first by using a Euclid algorithm type of argument and get the GCD of the first row up in the first 1, 1 coordinate. Then using that 1, 1 coordinate, we can clear and we can multiply it by the needed quotients and multiply the first column by that quotient and subtract the jth column by this multiple. So that way, all the other entries on the first row would end up being 0. Then we do the same for the first column and take the GCD of the components in the first column, put it in the 1, 1 coordinate, and clear the first column. So all together, we get a matrix that has only one entry at the 1, 1 position, and the rest of the entries are 0. And we can repeat this argument again by doing this process for the block below this. So after that, we can do further manipulation and make sure that the GCD of all the diagonal entries are in the 1, 1 position and so on. The way that we did it was by taking the minimum of the norms among all the matrices that we can achieve, the minimum of the norms among the non-zero entries of all the matrices that we can achieve, and put it in the 1, 1 coordinate, and then we show that this should divide all the other entries in the first row and the first column, and we did as I explained. So the whole process is quite algorithmic, and that can help us to solve equations of the form AX equals to B over a Euclidean domain. If we just ask for an existence kind of result and relax this condition and allow every invertible matrix with entries inside D, GLN of D, and relax this one and allow every invertible matrix, M by M matrix with entries inside D, GLN of D, then in fact this result holds not only for Euclidean domains, but also for PIDs. And the argument has some similarities with what we have done here. The only point being that we need to show this for the 2 by 2 matrix. After showing it for a 2 by 2 matrix, then we can repeat the argument that we have over here. But let's continue and see the result that we have proved for Euclidean domains. What kind of implications can it have? How can it help us to get a better understanding of modules, let's say. In fact, we got back to equations after describing what modules are and studying Noetherian modules. We got back to linear equations, system of linear equations, after we proved that every finitely generated R module M, when R is a Noetherian ring, is isomorphic to the co-kernel of some rectangular matrix. Okay, so again, let me repeat, because this part is important. We started with a finitely generated R module and showed that such a module is isomorphic to the co-kernel of a rectangular matrix if my R module is Noetherian. In fact, we showed that when R is Noetherian, every finitely generated R module is also a Noetherian R module. Using that result, we showed that such a module is isomorphic to the co-kernel of some matrix. And let's recall, co-kernel of a matrix is, by definition, the codomain mod out by the image of A. So the co-kernel tells us how far our matrix is from being surjective. The same as kernel is a measurement of how far our matrix is from being injective. Co-kernel tells us how far it is from being surjective. So now what we proved is that every finitely generated R module, when R is a Noetherian ring, is isomorphic to the co-kernel of some rectangular matrix. Now, what we will do next is to use existence of a Smith normal form, apply that for this particular matrix that we get for this finitely generated R module, at least when there exists such a thing, namely when I'm working with a Euclidean domain, let's say, and then use that in order to get a classification of finitely generated R modules. Okay, let's see how the argument goes and where we get to. But in order to do so, I need to understand the connection between co-kernel of a matrix A and co-kernel of another matrix A prime, assuming that I can get from A to A prime using row and column reduction operations. So let's make it even a bit more general. Assume that I give you two matrices, rectangular matrices of the same size, and suppose that A prime is A multiplied by invertible matrices from both sides. So here I'm allowing U and V to be any invertible matrix. So I'm not asking them to be inside E sub n plus minus R or E sub n plus minus R. I'm allowing a bit more operations. I'm allowing multiplication by every invertible matrix from left or right. If this is the case, then the co-kernel of A is isomorphic to the co-kernel of A prime. And of course, this would imply that if A is in the same equivalence class, if I can get from A to A prime using row and column reduction operators, then of course, I'm going to get these U and V, and therefore this star holds. Okay, so let's see how the lemma goes. It's actually rather easy lemma, but it is important because it gives us a connection between the co-kernel of a rectangular matrix and the row and column reduction operators. So suppose that I have this equality, A prime is UAV, and I need to understand the co-kernel, and that means I need to understand image of A prime and be able to compare it with image of A. So what is image of A prime? It is A prime times an arbitrary vector in R to the n. Okay, now what is A prime? The assumption is that A prime is U times A times V, where U and V, both of them are invertible matrices. Now, because V is invertible, V times R to the n is nothing but R to the n. I can just replace this by R to the n, knowing that V times R to the n, knowing that V is a surjective map, I can deduce that it is simply R to the n. Now I multiplied by A and then multiplied by U. Now A times R to the n, by definition, is image of A. So image of A prime is this invertible matrix times image of A. So that's good. So this means that at least image of A prime and image of A, they are isomorphic because I'm applying an invertible R module homomorphism, an invertible a matrix with entries inside the ring R. I'm applying that to this module and I'm getting the other one. So they are the same modules. They are isomorphic modules. They are not the same. They are isomorphic modules. Now I need to understand the co-kernel, but that's an immediate consequence of the fact that X going to UX is an R module isomorphism, which sends the denominator of co-kernel of A to the denominator of the co-kernel of A prime. What do I mean by that? So now if I apply this U to the coset that's represented by X, this coset, this element belongs to the co-kernel of A. Now I'm applying U to this element of the co-kernel of A, and where does it go? It goes to UX plus U applied to this submodule. But U applied to this submodule is image of A prime. So I'm getting UX plus image of A prime, an element of the co-kernel of A prime. So I'm getting an isomorphism, an R module isomorphism from co-kernel of A to co-kernel of A prime. So I'm showing that these co-kernels are isomorphic as we wanted. And as I've mentioned earlier, when A is equivalent to A prime, then A prime is U times A times V for some U in the group generated by elementary matrices and permutation groups, and V the same. In particular, U and V, both of them are invertible matrices. So the claim follows from the first part that we showed. So this means that if I use row and column reduction operations and go from matrix A to matrix A prime up to isomorphism, I'm not changing co-kernel of the matrices. Now let's go back to the question of classifying finitely generated R modules, at least when I have a nice representative in the equivalence classes of A's up to row and column reduction operations, namely Euclidean domains. Suppose, so again, I'm trying to classify finitely generated modules over Euclidean domains. So suppose D is a Euclidean domain and M is a finitely generated R module. Now, claim is that every such module is isomorphic. For every such module, you can find some non-negative integer n and some elements of the ring, this Euclidean domain D. Let's denote them by D1, D2, dr, so that D1 divides the next one, D2 divides the D3, and so on. And what's the connection between these D sub i's and n and m? The module M. Module M is isomorphic to this D to the n copies of D, Cartesian product with D over the ideal generated by D1, Cartesian product with D divided by mod by the ideal generated by D2, and so on. Here we are thinking about the right-hand side as a D module, but notice that the right-hand side is also a ring, but here we are thinking about it as a D module. So This gives us a very concrete understanding of every finitely generated D module as long as D is a Euclidean domain. Let's see how the proof goes. A Euclidean domain is a PID that we have proved long ago. Every PID, every ideal in a PID is a principal ideal. That's the definition. In particular, every ideal is finitely generated. It is in fact generated by a single element. And therefore, every PID is a Noetherian ring. So altogether, we are saying that every Euclidean domain is Noetherian. Now, we have proved that when I give you a Noetherian ring and a finitely generated module over this Noetherian ring, then this finitely generated module is isomorphic to the co-kernel of a rectangular matrix. So there exists a rectangular matrix such that this module M is isomorphic to the co-kernel of this rectangular matrix. Now, we know by the previous lemma that the co-kernel of this matrix is isomorphic to the co-kernel of every other matrix that we can get to using row and column reduction operations. But we have proved existence of a Smith normal form. That means we can get to a Smith normal form of the matrix A sub M. And by the previous lemma, that should have the same co-kernel. So let's record what I just said, recalling what a Smith normal form is. Smith normal form of a matrix is of this form that I have a block of diagonal matrix and zeros everywhere else, and the diagonal entries have this property that the first one divides the next one divides the next one, and so on. And we can get from this matrix to this one using the row and the column reduction operations. So in particular, by the previous result, the co-kernel of A sub M, which is isomorphic to M, is also isomorphic to the co-kernel of this nice matrix. Now, what is co-kernel of this matrix? Co-kernel of every matrix is isomorphic to its codomain, modeled by its image. Now, what is image of this? So this means I need to apply this to an arbitrary vector, and I need to understand what kind of vector I'm going to get. So when I apply it, of course, these components will be always 0. Now, when I apply this to and multiplied by some vector, the first component is multiplied by d1. The second component is multiplied by d2. The rth component is multiplied by d sub r, and the rest of the components are multiplied by 0. So this means that I'm going to get a vector whose first component is inside the ideal generated by d1. Second component belongs to the ideal generated by d2. And starting from the r plus 1th component, I'm going to get just 0. So this is the image of this nice matrix. Now that I understand the image, I can understand its co-kernel. So altogether, we get that M is isomorphic to the module M is isomorphic to the co-kernel of A sub M. Co-kernel of A sub M is isomorphic to the co-kernel of this nice matrix, because I can get from one to another using row and column reduction operations. And this one is isomorphic to its codomain divided by its image. And it's easy to see that if I send the numerator to the corresponding cosets, then the kernel would be precisely what we have over here. So by the first isomorphism theorem of modules, we get this isomorphism. So altogether, we get the desired isomorphism, that an arbitrary finitely generated D module is isomorphic to D over the ideal generated by D sub 1, Cartesian product with D over the ideal generated by D sub 2, and so on. And at the end, we have n copies of D. So n refers to the number of columns that we have over here. So that completes the proof. Now let's look at special cases of D. For instance, what happens when D is Z? Of course, Z is a Euclidean domain. Another example that we have for Euclidean domains is the ring of polynomials with coefficients inside a field, f bracket x. Let's see what kind of consequences do we get in those cases. Let's start with ring of integers. So applying this result for ring of integers, we immediately get the following theorem. Let's recall that a Z module is an abelian group and vice versa. An abelian group is a Z module. So there is no distinction between Z modules and abelian groups. They are the same. A Z module homomorphism is an abelian group homomorphism and vice versa. So that helps us to come up with a classification for finitely generated abelian groups. So what is the result? Every finitely generated abelian group is isomorphic to Z to the n Cartesian product with the cyclic groups of order D1, cyclic group of order D2, cyclic group of order D sub R, where D sub i's are positive integers and the first one divides the next one and so on. Every finitely generated abelian group in particular is Cartesian product of a bunch of cyclic groups. In fact, we have a bit more control on them, but let's say it like this. Now let's go through the proof. Again, every finitely generated abelian group is a finitely generated Z module, because we have discussed this, that every abelian group is a Z module, and the way that we can generate an abelian group is exactly the same way that we can generate a Z module. So every finitely generated abelian group is a finitely generated Z module. Now Z is a Euclidean domain. So I can apply the previous theorem, the classification, a classification of finitely generated D modules where D is a Euclidean domain. We can apply it in this setting, and we end up getting some non-negative integer n and some integers, non-zero integers, such that D1 divides the next one, divides the next one, and so on. Now, what's the connection between this and the finitely generated abelian group? Nothing special. A is in fact isomorphic to Z to the n Cartesian product Z mod out by the ideal generated by D1 and so on. Now, notice that the ideal generated by D1 is the same as the ideal generated by negative D1. So without lot of generality, I can assume that these D sub i's are positive. When I change the sign, this divisibility condition doesn't change either. At the end of the day, these divisibility conditions are in terms of the ideal generated by D1, ideal generated by D2, and so on. And so if I replace D sub 1 by another generator of the ideal generated by D sub 1, I'm not losing I'm not adding any condition, and the same statements hold. So D sub i's are positive integers, and each one divides the next one. In that case, the Z mod out by the ideal generated by D sub 1 is nothing but the cyclic group generated by the cyclic group of order D sub 1 and so on. So that altogether we get the desired result that an abelian group A, if a finitely generated abelian group A, is isomorphic to Z to the n Cartesian product a cyclic group of order D1, Cartesian product cyclic group of order D2, and so on, where D sub i's each one divide the next one. That completes the proof. In particular, if I just tell you that I'm giving you a finite abelian group, of course it's going to be finitely generated, because I can think about it as an abelian group generated by all of its elements. So you're getting a finitely generated abelian group. Therefore, I can apply this result over here and say that this finite abelian group should be isomorphic to this kind of group for some non-negative integer n and some D1 dividing D2 and so on. But when I start with a finite abelian group, I cannot have Z to the n here unless n is 0. So I can drop this factor completely, and I end up getting these factors. So this means altogether, every finite abelian group is isomorphic to Cartesian product of cyclic group of order D1, cyclic group of order D2, cyclic group of order D sub R for some positive integers D1 dividing D2 and so on. So in fact, here I can go further and assume that D sub i's are at least 2, unless my finite abelian group is trivial. So this was one of the classification. This is a classification of finite abelian groups that I've mentioned earlier. Now, having this classification in hand, one can prove that dual of every finite abelian group is isomorphic to itself. But notice that because this classification is not quite canonical, this isomorphism that we get here is not canonical. So you cannot give me a concrete kind of isomorphism from A to A hat, the way that we got it from A to the dual of the group A. So in a sense that if I tell you there is a group homomorphism from A1 to A2, you cannot give me a whole isomorphism over here that would be compatible with a group isomorphism, a group homomorphisms that you're giving me from A1 to A2. But disregard this if you get confused a bit, but that's okay. This is an excellent exercise. Try to show that dual of a finite abelian group is isomorphic to itself using classification of finite abelian groups. So if A is a finite abelian group, show that it's isomorphic to its dual. Okay, so now we saw how strong our theorem about classification of a finitely generated modules over a unique Euclidean domain is. As a particular case, we got a classification of finitely generated abelian groups and finite abelian groups. Now let's see how much more we can get out of it by looking at the example when D is F bracket X. So we will see that the result that we got is going to give us very strong results on linear algebra. So in fact, we will be proving existence of the so-called rational canonical form of a matrix using the classification result that we have already proved. But let's prepare a bit before we get to that proof. So I'm going to go over basics of linear algebra, especially because we are going to work with an arbitrary field. It is better to go over these basics that you have already seen in your linear algebra course, mostly over complex numbers or real numbers, but the ideas are completely similar. So let's review these results, some of these results, especially the connection between a linear transformation and matrices. So suppose F is a field and V is a finite dimensional vector space over this field. Now, T is called either an F linear map, or you can also think about it as an F module homomorphism from V to V. So that means it's an abelian group homomorphism and it preserves scalar multiplication. Now, for a given basis of this vector space, it's a finite dimensional vector space, so we have proved existence of basis for finite dimensional vector spaces, and we showed that the cardinality or the number of vectors is independent of the choice of basis. We call that dimension of V over F. So suppose that B is a basis for this vector space. Now, knowing that every other vector is a linear combination of these v sub i's in a unique way, we can associate a column vector to every vector in the vector space V. In fact, we use this to show that every finite dimensional vector space is isomorphic to f to the n, where n is the dimension of V over f. So again, let me repeat this part. Assuming that I have a basis B consisting of n elements, we get an F isomorphism. That means that I'm thinking about them either as F vector spaces or F modules from V to column vectors. We can also think about this as F to the n, but I'm now thinking about it as a column vector, the set of column vectors. Now, what is this isomorphism? You give me your favorite vector, and I'm going to write it in terms of the vectors inside the basis B. This is an ordered set, so I'm going to write it in terms of V1 to the dot Vn, and coefficient of V sub I, let's call it C sub I put it in the ith component of this column vector that I'm supposed to give you. So again, for every vector V, I'm going to write it as a linear combination of V1 to the dot Vn, because Vi's span and the entire V I can do. There is such a linear combination, and because V sub i's are linearly independent, such a linear equation is unique. Such a linear combination is unique. So there are unique C sub i's in F so that this equality holds. Now I'm going to define V square brackets sub B. We are going to define this to be the column vector that consists of these coefficients. Now the map from the vector space V to column vectors with coefficients with entries inside the field F that sends V to this column vector is an F isomorphism. It is F linear. It's an abelian group homomorphism. It preserves scalar multiplication, and it is surjective, and it is injective. And we have already proved this when we were discussing existence, and we proved existence of a basis. So this map is an F isomorphism. This is how we can encode understanding of a vector space V using n elements of the vector F. So again, from this point on, instead of writing this n column vectors with n entries, I will simply write down F to the n with an understanding that I'm thinking about F to the n as column vectors. Now that we have encoded the entire vector space using these column vectors, we can also try to encode a given linear transformation. So suppose that T is a linear transformation, the one that we have been given. Now, because every other vector inside this space is a linear combination of V sub j's, and T preserves linear combinations, it would be enough to understand what T does to the elements of the basis. So if I understand T applied to V sub j for an arbitrary j, then I can write down what T does to any linear combination of V sub j's. And that means I can understand it for every vector inside this vector space. So that would be a good way to encode the action of T. So I apply T to V sub j. I'm getting another vector inside the vector space V. That means I can write T applied to V sub j as a linear combination of V sub 1, V sub 2, V sub n. So there are entries, elements of the field F, so that T applied to V sub j is T sub 1, small t, sub 1j applied times V sub 1 plus T sub 2j times V sub 2, T sub nj times v sub n. So we are applying the operator t to v sub j and then writing it as a linear combination of v sub i's. And because I'm applying it to v sub j, I want to make sure that I know that I have applied it to t sub j. And then the coefficient of v sub I is denoted by small t sub ij. So altogether, I can put all these t sub ij's in a matrix form, and I put t sub ij in the ij entry of a matrix, and I'm going to denote it by square bracket t sub b, and that would be my matrix. Now, if you think about it, the jth column of this matrix are precisely, I mean, the jth column consists of these elements of F. So the first entry in the jth column is t sub 1j, the second one is t sub 2j, and so on. And at the same time, this is the same as saying what this vector is in the base B. So what I'm saying is that the jth column of this matrix that I'm introducing is nothing but what the vector t applied to v sub j is with respect to this basis. Now, again, jth column of a matrix is the same as the matrix times the standard vector that has 1 in its jth component and 0 everywhere else. And at the same time, that is what v sub j is with respect to this basis. So if I want to write down what v sub j is in this basis, okay, I need to write down v sub j as a linear combination of v sub 1 v sub n. That means I need to put 0 everywhere except the jth entry. So v sub j in the basis v sub 1, v sub 2, v sub n is nothing but the standard basis, meaning I have this column vector that has 1 in its jth component and everywhere else is going to be 0. Now, again, let's go back to the operator t. When I multiply the matrix of square bracket t, this matrix, and I multiply it by this standard column, which is the same as this one, I end up getting the jth column of this matrix. The jth column of this matrix is t applied to v sub j written in this basis. So I get this equality. So for every j, when I multiply this matrix by the vector that v sub j gives us, it's the same as the vector that I get after applying t to v sub j. Now, because multiplication by this matrix is a linear operator, and applying t is a linear operator, and applying these square brackets is these square brackets again, these are linear isomorphisms between v and f to the n. Altogether means we end up getting that this equality holds for every vector v. So we get that when I apply t to any vector that you give me, and I write this in base b, it's the same as writing v in base b and multiplying it by this matrix that we got from encoding the linear action of t, the linear operator t. So now what we are getting is that for this linear operator t, after I encode it in terms of the basis b, the action can be encoded by matrix multiplication using the matrix that we have introduced over here. So we use this kind of square bracket to encode v, this arbitrary matrix, vector space with f to the n. Now this encoding is also compatible with encoding of linear operators with the matrices and matrix multiplication. We can understand it via the following diagram, and saying the following diagram is a commutative diagram. So given V, we have introduced this kind of linear operator, linear isomorphism between V and the column vectors f to the n. Now, when I give you a linear map from V to itself, I can go from V to f to the n again. Now the question is, can I complete this diagram? So this T is given to me, this isomorphism we understood, essentially using a basis B, I can encode every vector and see what kind of linear combination we get. And now by the discussion that we had, in the bottom, we are going to get only multiplication by this matrix that encodes the operator T. So this diagram is a commutative diagram. So if I start with V over here, I can go here, I get TV, and then I come down here. That means I need to write down what TV is with respect to the base B. But I can also go down over here, and I get the vector V written in the base B. And then this gives me what the matrix T, the matrix associated with the operator T times this vector gives me. So I get this equality. So this is a pretty good diagram to remember the connection between linear operators and matrix multiplications. Okay. This means that when I give you a linear operator, you can choose your favorite basis and encode the action of this linear operator in terms of a matrix. Now, from computational point of view, if this matrix is as sparse as possible, then it would be much better for us. Now, what does sparse mean? So if this matrix has many zeros, then of course, when I want to multiply it by another matrix, let's say, or when I want to apply it to a vector, then it's much easier for us from computational point of view. And not only computational point of view, but also from theoretical point of view. So if there are much less non-zero entries, we can get a better understanding of how T actually acts on this space. So for instance, if it was a diagonal matrix, then it's much easier to understand what powers of that matrix would be. So that essentially means that I have to raise every one of the diagonal entries to that power. So altogether, what I'm saying is that it would be better for us to be able to find a nice basis for this operator so that the matrix form that we are getting, we call it a matrix representation of this linear operation, linear map. So if we can find a sparse matrix representation of T, then that would be nice. That would be good from many angles, both computation and computational point of view and a theoretical point of view. So our next goal is to find a sparse matrix representation for a given linear map T. Now, before doing so, getting more involved with finding a sparse matrix, let's try to understand connection between two such matrices. So I give you a linear map. I have the possibility of choosing different bases, and I end up getting different matrix representations based on the bases that we have chosen. Now, the question is, what is the connection between these matrices that we are going to get? What is the connection between different matrix representations of a given linear map? So suppose I give you two bases. One of them is B, and the other one is B prime. The first one consists of vectors v1 dot dot vn, the second one v1 prime dot dot vn prime. We have already proved that they should have the same cardinality, so n is the same in both of them. That's the dimension of v over f. Now, I can write down any vector that you give me either in terms of the basis that's given by b, or in terms of the basis that's given by b prime. So I end up getting two different vectors. The question is, what's the connection between them? Now notice that because v sub i's are linearly independent, I can send v sub I to an arbitrary vector and extend it to an F-linear map. Because v sub i's are linearly independent, I can do that, so I choose to send them to v sub I prime. Because v sub I primes span the entire V, this map is surjective. Because v sub I primes are linearly independent, this map is injective. So altogether, we get that there is this isomorphism, there is this vector space isomorphism from V to V that sends elements of the first basis to elements of the next basis. So this is an isomorphism that sends v sub I to v sub I prime. Now, let's see what this S does when I put it in this diagram. So v sub I over here goes to the standard vector E sub I, where the ith component is 1 and the rest are 0. When I apply S, I end up getting v sub I prime. Now, when I write down v sub I prime with respect to the basis B prime, I get the same standard vector. And that's the identity map. So I can go from F to the N to F to the N with the identity map. So that means that I'm getting this commutative diagram. That means, because I showed it is commutative only for the elements of the basis, but everything is linear. So that implies that this is a commutative diagram for an arbitrary vector V. So again, what does that mean? This means when I apply S to V and write it in V prime basis, it's the same as looking at V in B base. But by the discussion that we had earlier, this can be viewed as a matrix multiplication. So the matrix that encodes multiplication applying S with respect to the basis B prime multiplied by writing V in terms of the basis B prime gives us the vector V with respect to the base B. So that's how we can change from one basis to another one. Essentially, by this type of matrix multiplication, I can change from the new base to the old one, or I can switch the order, multiply by the inverse of S, and so on. Have this in mind. Our question was about different matrix representations. So far, we have only worked with the vectors. Now the question is, can I use this to understand different matrix representations for a given linear map T? So we are given a linear map T from V to V. I can use either the base B or base B prime in order to encode the action of T using matrix multiplication. So this is one matrix representation for the linear map T. This is another matrix representation for the linear map T. Now, what we showed over here is that when I apply B or B prime and go from V to F to the N, then the map between them is essentially identity if I apply S in the middle. So let's try to understand this. So when I go from a V to V, okay, when I go from V with respect to the B base to F to the N, and then with respect to the B prime base to F to the N, again, let's go back here again. Here, this part was identity, but this part was S. Now I want to switch it. I want to start with identity over here, the same V. I want to come down and then come down here, or I want to use B prime and go down, but I want to put identity in the middle for V. Now, what should I put here? Now, if you think about it, this identity map over here is the same as if I put identity in between V's, it's like multiplying this guy by inverse of S, the matrix that S gives me with respect to B prime. That's exactly what I'm writing over here. That's instead of going, so when I want to go from F to the N to F to the N and get a commutative diagram, we have to multiply. So again, let's make sure that you understand it. We know that V written in base B prime, when I multiply it by the matrix S encoded with respect to the base B prime, I get V written with respect to the base B, basis B. That means this. So I start with V, I apply this, I go to F to the N. When I multiply it by S B prime, I get exactly what I get as I write the same vector with respect to the basis B. So that means that this is still a commutative diagram. So I can multiply it by this matrix and go from bottom to top. So it's like an elevator by multiplying by this matrix. I can do the same from the other one, from the other side. And the whole thing is commutative so far. In particular, instead of going from F to the N to the F to the N, just multiplying by the encoding of T with respect to the basis B prime, I can go up, go this way, and then come down. What does that mean? Let's try to understand it. I given a column vector in F to the N. First, we multiply by this guy. Then we multiply by the matrix encoding T with respect to the base B. Then we multiply by this matrix, inverse of this matrix. And that gives us the same multiplication by this one. So that means the matrix representation of T with respect to the basis B prime is equal to this multiplication of inverse of this changing basis operator, changing basis matrix. The matrix representation of T with respect to the basis B times this matrix, changing basis matrix S. If you remember this kind of thing, we say conjugate of this matrix. So if when I start with a matrix A and multiply it by matrices B and B inverse, B and B inverses, so let's say B inverse B, we call this a conjugate of the matrix capital A. So what we are showing is that two matrix representations of a given linear transformation are conjugate of each other. And one can show the other way around as well. So if I happen to know that two matrices are conjugate of each other and think about this matrix multiplication as a linear transformation, then it's the same as saying that this linear transformation have these two different matrix representations with respect to two different bases. So this is kind of if and only if two matrices are conjugate of each other, if and only if they are matrix representations of some linear transformation. And if I give you a linear transformation, all matrix representations of this linear transformation are conjugate of each other. Okay, so now this question about finding a sparse matrix representation for a given linear transformation can be viewed as finding a sparse conjugate for a given matrix. So I can start with a linear operator, write it in respect to some basis, write down some matrix representation. Now I'm asking myself, what is a possible sparse conjugate of this matrix? And that's equivalent to asking, what is this? What is a possible sparse matrix representation for the linear transformation that we have been given? So both these points of view are important. So either way, we are looking for a sparse conjugate for a given matrix, or we are looking for a sparse matrix representation for a given matrix. Now, similar to the case of algebraic numbers, where we saw that instead of understanding zeros of polynomials, we looked at that zero alpha and then evaluated every other polynomial at that alpha. And then we thought about what ring theory can imply. And we understood the kernel, we tried to understand the image, and so on. We do the same here. We want to understand this linear operator T from V to itself. Then what we do? What do? We evaluate every polynomial at T, similar to the case of zeros of polynomials. So we evaluate polynomials at T. What does that mean? So in the case of zeros of polynomials, we assume that the zero belongs to an ambient ring, and then we evaluated, we substituted this for the elements. For the case of linear operators, we can do two things. Either I can introduce a ring, or we can first start by understanding naively what f of t means, where f is a polynomial with coefficients inside the field capital F. So suppose f is given by the coefficients a sub i's. That means f is a sub m x to the m plus a sub m minus 1 x to power m minus 1, and so on, where a sub i's are elements of the field capital F. Now I'm going to substitute t for x. So I get f of t is a sub m t to power m plus a sub 2 t to the power m minus 1, and so on, till I get to a sub 0, and I forgot to write identity over here, or I, for the identity operator. So f of t being this means what? I need to give you a linear transformation from V to V. That means f of t. So this f of t is supposed to be a linear transformation from V to V. That means when I give it a vector V, what is the outcome? I apply this guy to V, multiplied by a sub n. I apply the next one to V, multiplied by a sub m minus 1. The last one is identity. When I apply to V, I get back V multiplied by a sub 0, and then just add them. And I get another vector inside the vector space V. So f evaluated at t is still an f-linear map from V to V. Now, if I write down the set of all f-linear maps, if I consider the set of all f-linear maps from V to V, then we denote this set by END sub f of V, the set of all endomorphisms of V. That's this end stands for endomorphisms. Endomorphism means homomorphisms that have the same target as as their domain. So all F homomorphisms from V to V are called endomorphisms. Now I'm considering the set of all F endomorphisms for the vector space V. Now it is rather easy and interesting to show that in fact the set of all F endomorphisms of V with respect to addition and composition is a ring. It is a unital, mostly non-commutative ring. In fact, this ring is isomorphic to the set of n by n matrices with entries inside the field F. And what is the isomorphism? I give you an F linear map from V to V. You choose your favorite basis. It doesn't matter what it is. And with respect to that basis, you are going to encode this linear map. So you send T to the matrix that we get with respect to the basis B. And it's easy to check that this map is in fact a ring isomorphism. It's an F linear ring isomorphism. So in particular, now you see, maybe more clear than before, that this is indeed a unital ring isomorphism. It's a unital ring and mostly non-commutative. And moreover, you can see that dimension of this ring is a vector, F vector space, and dimension of this is precisely dimension of V squared. In particular, it's a finite dimension vector space over F. Now, when I say evaluate this polynomial at T, it is precisely the same as saying that I'm considering the evaluation map from the ring of polynomials to the ring of endomorphisms of the vector space V, where when I feed it a polynomial F, it just evaluates that polynomial at T and gives me an endomorphism from V to V, exactly the same way that we have described. And this map, as before, is an F linear ring homomorphism. The argument is identical to the case of algebraic numbers, where we substituted a variable by some element inside the ring extension. It didn't even have to be algebraic. So we defined the evaluation map or substitution map for arbitrary ring extensions, and the same argument works here identically to that case. So this is a ring homomorphism. Whenever I give you a ring homomorphism, you can ask what is the image, what is the kernel. So by the first isomorphism theorem, we have that the ring of polynomials modeled by the kernel of this evaluation map is isomorphic to its image, and the image is definitely a subring of endomorphisms of V. In particular, the image, which is an F subspace of this ring or this vector space, is a finite dimension. This is finite dimensional. This is infinite dimensional. So the kernel cannot be zero. Definitely, I have a non-zero polynomial that vanishes after I evaluate, after I substitute T for my variable. So kernel of this ring homomorphism is a non-zero ideal of the ring of polynomials with coefficients inside the field F. But F bracket X is a PID. It's a Euclidean domain, and therefore it's a PID. Kernel of V sub T is a non-zero ideal. And let's also notice that the scalar maps from V to V, these are always in the image of the evaluation map. Simply when we evaluate the constant polynomial, we end up getting these scalar multiplications. So the image of V sub T is not the zero ring. it has at least the scalar multiplication or the identity map inside its image. So that means that phi sub t, the kernel of phi sub t cannot be the entire ring f bracket x. It's a proper non-zero ideal of the ring of polynomials with coefficients inside the field f. That means I can find a non-constant because it's not the entire f bracket x. The generator cannot be a constant. It's a non-constant because it's not zero and it's not the entire thing. It's not constant. And I can always multiply it by the inverse of the leading coefficient. That doesn't change the ideal. And I can assume that it's monic. So there exists a non-constant monic polynomial that we are going to denote by m sub t comma f, inspired by the minimal polynomial of alpha over f. We use the same notation here, so that the kernel of evaluating at t is the ideal generated by this unique monic non-constant polynomial m sub t comma f. This polynomial is called minimal polynomial of t, the linear operator t. Now, what is the main property? The main property is that this generates the ideal of the polynomials that vanish after I plug in t. Equivalently, if a polynomial after substituting t gives us 0, if p of t is 0, then p should be a multiple of m sub t comma f, and vice versa. If it's a multiple of m sub t comma f, then after evaluating it at t, we should get 0. So that's what we have proved about minimal polynomials of some linear transformation. Let's summarize it. So suppose that V is a finite dimensional F vector space, and T from V to V is an F linear map. Then there is a unique non-constant monic polynomial in F bracket X with the following property, that P of T is 0 precisely when the minimal polynomial divides P for a given polynomial in F bracket X. Okay, so now we have an understanding of minimal polynomials using basics of ring theory and the fact that F bracket X is a PID. Next, notice that this concept of minimal polynomials that we have defined for linear transformations, we can also define for matrices. And this concept, when we apply it for matrices, it doesn't change as we change the matrix from to a conjugate of the matrix. So this minimal polynomial of a matrix stays the same when A is changed to a conjugate of A. So this is what we are going to discuss next. Okay, so I give you a matrix with entries, a square matrix with entries inside F, and then matrix multiplication gives us an F linear map from column matrices to column matrices. So L is kind of for left multiplication. So I'm multiplying from left by the matrix A, and this is multiplied by a column vector. We end up getting another column vector. So F to the n here denotes the set of column vectors of size n. So I feed it an x and multiply it by a. I get another one, and we are denoting this by L sub a. Now, it's rather easy to see that this linear transformation, this is first of all a linear transformation, and when I apply it to the basis B, where B is the standard matrix, standard basis, when I apply to that, I get precisely the matrix A that we started with when I encode this linear transformation. Because if you remember, for a linear transformation T and a basis B, the jth column of this matrix is nothing but applying T to the jth entry, jth vector of the basis. Now, when I apply this guy to the jth vector here, that means I need to apply L sub A to E sub J. That means I need to multiply A by E sub J. I get the jth column of A. So we get this equality. So this means this L sub A is kind of the inverse of this bracket B isomorphism between endomorphisms of V and n by n matrices with entries inside F. Okay, so again, let's write down what I just said. So from the n by n matrices, we are giving a map to F automorphisms, F endomorphisms of F to the n, and the map is sending the matrix A to the left multiplication by A. We had already seen the other way from the ring of endomorphisms of F to the n to n by n matrices with entries inside the field F, simply sending T to the matrix representing T with respect to the base B. Now, what we showed here is that when we choose B to be the standard basis, one is inverse of the other one. But of course, I can choose another basis. Then what happens? The key point being that if this linear transformation is actually zero, after I substitute this at some polynomial, I end up getting zero, then it doesn't matter what basis you pick. No matter what basis you pick, when you write down the matrix representation of zero operator, you end up getting zero. And because writing it in basis B is a ring homomorphism, I can switch it with this. I can first write it in terms of the matrix and then substitute it, evaluate it, or first I can evaluate it and then look at the matrix representation. And considering that matrix representation of the zero operator is always zero, we end up getting that for every polynomial, when I evaluate the matrix representing T in the standard basis, this is zero if and only if the P applied to the operator T is zero. Then because L sub A and so on, the isomorphisms. And this being zero implies that the same equality is true for every matrix representation of the operator T. As again, the order of taking representative and or first taking the representative and then substituting, we can always switch the orders because choosing a representative, a matrix representation, is a ring homomorphism. So knowing that this is zero, I can deduce that this is zero. Knowing that this is zero, I can deduce that this one is zero for every basis P prime. Now, altogether, what am I getting? I can define minimal polynomial of a matrix. How? I give you a matrix, you consider this linear transformation attached to this matrix, and define the minimal polynomial of this guy to be the same. Define the minimal polynomial A to be the same as the minimal polynomial of this linear transformation. Now, when I choose a different basis, the matrix representation of L sub A would be a conjugate of matrix A that we started with, and vice versa. Every conjugate can be realized as a linear transformation, as a matrix representation of L sub A. That means what? That means that minimal polynomial of a conjugate of A is the same as the minimal polynomial of A. So altogether we get what we claim, that we can define minimal polynomial for matrices, and this concept doesn't change as we change the matrix to its conjugate. This polynomial doesn't change as we change the polynomial to its conjugate. So conjugation does not change minimal polynomial. Now, the next step, so far we have used this substitution and ring structure to get a better understanding of linear operators. Next, we go one step further. We use module theory to get an understanding of the linear operations and get a sparse matrix representation for a given linear map. So here is the key point. So pay attention here. I give you a linear map from V to V. We have already looked at the evaluation map from F bracket X to endomorphisms of V. Now I'm going to view V as an F bracket X module. So V itself is an abelian group. When I want to think about it as an F bracket X module, I need to define a scalar multiplication. So I give you a polynomial and a vector inside V, and I need to define F dot V. How can I multiply? What is this definition? I am going to substitute T for X and get an endomorphism for the vector space V. So I'm going to substitute or evaluate F at T, get an endomorphism of the vector space, and then plugging V into this in the endomorphism to get another vector inside V. So altogether, F dot V is going to give me this new vector inside the vector space capital V. And what is this new vector? I evaluate the polynomial F at T, get an endomorphism of the vector space, and then feed it the vector V. That's the operation that we are defining. Now let's check some of the properties. Why is this a scalar multiplication? Let's check some of the properties. So for instance, when I look at F1 dot F2 dot V. Now what is this? This is F1x dot, and the guy inside, I need to evaluate F2 at T and then multiply it by V. And this one is evaluating F1 at T. Now evaluation at T is a ring homomorphism. So we get that this side is nothing but phi sub T of F1 times F2 applied to V. That's precisely F1 times F2 dot V. So altogether, let me write it over here. So this bottom one is the same as, this bottom one is equal to phi sub T, because phi sub T is a ring homomorphism, this is the same as this one. And that's by definition F1, F2 dot V. And that's exactly what we wanted to show. We started with F1 dot F2 dot V and end up getting that it is F1, F2 dot V. Now distribution properties are rather easy, again, because phi sub T is a ring homomorphism and linear operations or matrix multiplications, they are distributed from both sides. It's a good exercise to write down the details and make sure that it is indeed a scalar multiplication, but it is rather straightforward. So I leave it to you to check all the details. So this is indeed a scalar multiplication. Now, if V is a finite dimension, then if I take an F basis, then as an F linear span of those vectors is going to give you the entire V. Of course, F bracket X module generated by those vectors would be the entire V as well. So that means what? That means V is a finitely generated f bracket x module. So we end up creating and viewing this finite dimensional space as an f bracket x module. Remember, f bracket x is a Euclidean domain, and therefore we are in a good place to use classification of finitely generated modules over Euclidean domains. We will do this in the next lecture and see what we get for the linear transformation.